Dear friends, myself is Dr. Neej Trivedi. I am going to take your lecture number 8 related with the flip-flop memory elements. This is in a paper EL 4502, that is unit number 3, flip-flops. Dear friends, we have studied a various type of the flip-flops, that is RS flip-flop, JK flip-flop, D flip-flop, T flip-flop, etc. with edge triggering, with level triggering and gated RS flip-flop and pulse triggered master slave flip-flops. So we have studied so many flip-flops and we can utilize them as the memory elements. Now, what happens? We have also studied the design of sequential logic circuits. Now suppose, think about like this. If you have designed some sequential logic circuit with one type of the flip-flops, and thereafter if you want to implement that circuit practically, then you will check your store or you will buy the available flip-flops from the market, and that flip-flop is not matched with your design problems. In design, you have utilized one type of the flip-flop, and in a market or store there is another type of the flip-flop is available. Then what you have to do? Either you have to redesign the problem with the available type of the flip-flops. But in that case, if the circuit is very complex, then this thing is going to be very difficult. Rather than that, there is another solution is this. You have designed a circuit with one type of the flip-flop, and in a market another type of the flip-flop is available. So whatever available flip-flop is there, that you convert according to your flip-flop requirements in your design problems. So conversions of the flip-flop is needed. And how to convert a one type of the flip-flop into another type of the flip-flop, that we are going to study here using synthesis examples. So we are starting with conversions of the flip-flops. Knowledge about how flip-flop of one type can be converted to another may be useful on various count. Say, when we have designed the circuit with one type and for implementation we get a different type from the store or a market. Redesign of the problem with available type of the flip-flop may take considerable amount of time if the circuit is very complex and it is inconvenient. Instead of that, one can convert the available type using few basic gates to the type in which design is done and implementing the existing design. That means if we redesign the problem using available flip-flops, then it will take a considerable amount of the time. Rather than, it is easier to utilize the available flip-flop in place of the design flip-flop using some conversions, using some basic logic gates, etc. And we can utilize this available flip-flop in design problem with modification. So conversions of the JK flip-flop to the SR, D and T is fairly straightforward, as we see from their respective truth table or characteristic equation. Now the question is this: if the available flip-flop is going to be JK flip-flop, and you have designed the problem with SR flip-flop, D flip-flop or T flip-flop, then the conversions from JK flip-flop or utilizing the JK flip-flop as SR flip-flop, D flip-flop and T flip-flop is very straightforward, or it is very easier, because you can see that from the truth tables or characteristic equation of SR, D and T flip-flops. In SR flip-flop, what is the no change conditions? 0, 0. In JK flip-flop also, no change condition is going to be 0, 0. In a SR flip-flop, set condition is going to be S is equal to 0, R is equal to 1. In JK flip-flop also, J is equal to 0, K is equal to 1. So reset condition is also going to be the same. Similarly, for the set condition is also going to be the same, 1, 0 condition for SR flip-flop as well as for the JK flip-flop. Only the last condition is different, that is 1-1 condition. In SR flip-flop, 1-1 condition is forbidden condition and it is accepted that never to impose these conditions. So when you design the circuit with the SR flip-flop, you might have taken the care that 1-1 condition, input condition is not going to be occur. So instead of SR flip-flop, if you are utilizing JK flip-flop directly, then that condition is not going to be occur, and hence in place of the SR flip-flop, directly you can utilize JK flip-flop without any modification. So directly in a design, SR flip-flop may be there, but the same circuit can be implemented using the JK flip-flop without any alteration, and it will work properly. No questions. So this convergence for JK flip-flop to SR flip-flop is very easy and straightforward. Convergence of JK flip-flop to SR, D and T flip-flop is straightforward as we see from their respective truth tables or characteristic equation. For example, one need not to do anything extra to replace the SR flip-flop from a design if SR flip-flop is not available by the JK flip-flop. So you have designed with the SR flip-flop and SR flip-flop is not available in the market. You can directly utilize the JK flip-flop which is available in the market in place of SR flip-flop, and you can implement that circuit. This is because the truth tables are same except for input combination 1-1, which is in design with the SR flip-flop is taken care of not appear at the input side. So this last condition in a JK flip-flop 1-1 condition is allowed. But in SR flip-flop, if you have designed the problem with the SR flip-flop, then this condition is not going to be occur, and hence JK flip-flop directly can be implemented. Hence replacing SR flip-flop with the JK flip-flop does not pose any problem. However, the reverse is not true. You cannot make a reverse here. If you have designed with the JK flip-flop, you cannot directly utilize the RS flip-flop for that. It has to be modified something. In design with the JK flip-flop, there remains possibility of 1-1 appearing at the input side, and that combination of inputs is forbidden for the SR flip-flop. So if you have designed the sequential logic circuit with the JK flip-flop, then there is a possibility that you have taken care that J and K is equal to 1-1 condition has to be utilized. That is toggle mode conditions. The flip-flop is going to be toggling on every clock pulses. So this condition is required for the JK flip-flop. But in RS flip-flop, this condition is forbidden, and hence you cannot utilize directly SR flip-flop in place of JK flip-flop. You have to make some modifications. Again, comparing truth table or characteristic equation of JK flip-flop and D flip-flop, we say that putting an inverter from J to K, we get D flip-flop from JK flip-flop, where J is equal to D. And T flip-flop can be obtained from JK flip-flop by making T is equal to J is equal to K. So again, the JK flip-flop can be utilized as a D flip-flop, and it also can be utilized as a T flip-flop. How? In a D flip-flop, there is only one input, and that input is going to be D. And here, if there is a J and K input, between the J and K input, if there is an inverter is going to be placed, so J is equal to D is going to be possible, and K is equal to J dash because it is going to be complemented through the inverter. And that way, JK flip-flop can be utilized as a D flip-flop. So just like RS flip-flop is converted into the D flip-flop, JK flip-flop also can be converted into the D flip-flop using one inverter only. So it is converted from the two input J and K, it is converted into the single input J only, and that J input will behave like a D input. Similarly, if the J and K inputs are shorted, that means it is converted into the single input and it can be designated as a T input, then it will work as a T flip-flop or toggle mode flip-flops. Because J is equal to K is equal to 0 condition, that is called no change condition, and J is equal to K is equal to 1, that means it is toggle mode conditions, the flip-flop is going to be utilized. So directly JK flip-flop can be converted into the RS flip-flop, or it can be utilized as a D flip-flop using one inverter, and by shorting the two inputs it can be utilized as a T flip-flop. Now we'll see the reverse, that JK flip-flop can be converted into the or RS flip-flop is available flip-flop is with you, and you have designed the problems with the JK flip-flops. So you want to convert the JK flip-flop, SR flip-flop into the JK flip-flop through some systematic approach. What is the procedure? What is the methodology for that? That we are going to study here. So here we show that how to convert an SR flip-flop to the JK flip-flop through a systematic approach as a general methodology for synthesis or design of the sequential logic circuit. A detailed study of various design problems and related issues are presented in chapter number 11. In step 1 of this method, we look into the JK flip-flop truth table and specially note that the transition from Qn to Qn plus 1 for a given combination of inputs J and K and present state Qn. So now we are interested in converting a RS flip-flop into the JK flip-flop, and we are going to see here the systematic approach methodology for that. And the first step of this method is to obtain a synthesis table. In this table, we look for the J and K flip-flop truth table, and specially note the transition from Qn to Qn plus 1 transition for a given combination of inputs Jk and present state Qn. That means we'll be writing the input conditions for the J and K inputs of JK flip-flops. And if we make a transition from Qn to Qn plus 1, what kind of inputs will be there? And for that, what is the inputs required for SR flip-flop? That means that we are going to get for excitation table of SR flip-flops. So in step 1 of this method, we look into the JK flip-flop truth table and specially note the transition of Qn to Qn plus 1 for a given combination of the input J and K and the present state Qn. Since the synthesis element is SR flip-flop, we shall refer to its excitation table to identify SR inputs combination required for a required Qn to Qn plus 1 transition. So this table is very important. Table 8.2 shows truth table of JK flip-flop as well as necessary SR input for Qn to Qn plus 1 transition. Such tables are also known as a state synthesis table. So what is the state synthesis table? This is one of the questions. This table shows the truth table of JK flip-flop as well as necessary condition for SR input for Qn to Qn plus 1 transition. That means excitation table of SR flip-flop as well as the inputs for the JK flip-flop to make a transition from Qn to Qn plus 1 is known as the state synthesis table. So we'll be starting that if the initial state of J and K inputs are going to be no change condition, J is equal to 0 and K is equal to 0. That is the no change condition for the JK flip-flop. It means that if the previous state is going to be 0, the next state is also going to be 0. You can see that in table. This is the Qn, that is the present state, and the next state is going to be Qn plus 1. So if the present state is going to be 0, after giving the clock pulse, the next state is also remains to be 0 because it is no change condition. Again, in the second row, you can see that J is equal to 0, K is equal to 0. If the present state is 1, after giving the clock pulse, no change, so the next state Qn plus 1 is equal to Qn only. If the third condition is given here, 0, 1, J is equal to 0, K is equal to 1, reset condition. Flip-flop is going to be reset if it is not reset. If it was reset, it remains to be reset. That means if this reset condition is given to the JK flip-flop, the previous state is going to be 0, that means it is reset. It remains to be reset. This means next state is also going to be 0. If the previous state is 1, it can be reset and it becomes 0. It makes a transition from 1 to 0. Then the fifth and sixth row, they are related with the preset conditions. J is equal to 1, K is equal to 0. That means set conditions. The flip-flop is going to be set if it is not set. If it is set, if it is already set, it remains to be set. That means if it is the previous state is going to be 0, the next state is also going to be 1. It makes a transition from 0 to 1. If the previous state was 1, it remains to be 1 because it is already preset, remains to be preset. Now J is equal to 1, K is equal to 1. These two conditions, 7 and 8 row, are for the toggle mode conditions. The flip-flop is going to be toggle. That means Qn plus 1 is equal to Qn bar. So on the next clock pulse, the output is going to be complemented from 0 to 1 and from 1 to 0. This way, these 4 columns of the state synthesis table can be prepared. Now, we'll see the excitation table for SR flip-flop making a transition from 0 to 0. You require S input is going to be 0 and R input can be 0 or 1, anything. That means 0, 0 condition or reset condition 0, 1. Combining these two conditions, you get 0x or 0 don't care condition is required. Similarly, to make a transition from 1 to 1, you require no change condition 0, 0 or 1, 0 condition. That means x0 condition is required. In excitation table, S and R input is required, x and 0. Again, 0 to 0 transition, 0x condition is required. You can see that from the first row, you can copy down. 1 to 0, from 1 to 0, that is a reset condition is required. S is equal to 0 and R is equal to 1 is required. From 0 to 1, that is a set condition is required. S is equal to 1, R is equal to 0 is required. Again, 1 to 1 conditions, that is x0 condition is required. 0 to 1, set condition 1, 0 is required, and 1 to 0, reset condition 0, 1 is required for SR flip-flops. This way, the state synthesis table for SR or to JK flip-flop is going to be prepared. Now, the next step is to write SR inputs as a function of JK inputs and the present state of JK inputs, Qn. So, we are going to prepare now the Carnot map of 3 variables. Which are the variables? JK and the present state Qn. These are the 3 variables. And we'll be writing the SR inputs as a function of JK and present state. Carnot map derived from the table 8.2 for SR input are shown in a figure 8.42 along with the design equations. So, J and K is having possibility 0, 0, 0, 1, 1, 1 and 1, 0. Qn can be 0 or 1. Combining these inputs, if you look this one, this table, J, K and Qn, these 3 variables. Starting from 0, 0, 0, that is called location M0, 0, 0, 1, M1, 0, 1, 0, M2, 0, 1, 1, M3, 1, 0, 0, M4, 1, 0, 1, M5, 1, 1, 0, M6 and 1, 1, 1, M7. These are the location in a Carnot map. Corresponding to that, what is the requirement for S that you can substitute in that places? M0 you can substitute 0, M1 you can substitute X, M2 you can substitute 0, M3 you can substitute 0, M4 you can substitute 1, M5 you can substitute X, M6 you can substitute 1, M7 you can substitute 0. This way, the Carnot map for S input can be prepared. And similarly, the Carnot map for the same location M0 to M7, X0, X1, 0, 0, 0, 1 can be placed. And this way, the Carnot map like this can be prepared for S input as well as R input. Now, using the method of simplification of Carnot map, we can simplify this one here. This is the sum of product equation. So we'll see that adjacent ones which are preparing a one pair, treating this don't care as a one, there is a maximum ones can be encircled is going to be only two real ones. So the Carnot map equation, sum of product equation for this, for Sn input is equal to the variable which j is having value j is equal to 1. K is having two different value 1 and 0, so the k variable will be drop out. Qn variable is having value 0, so Qn variable is going to be complemented. So we are having two variables, one is a Jn variable, the first variable is Jn variable which is having one value, so it is uncomplemented. And Qn is having 0 value, so it is going to be complemented. So the characteristic equation for Sn input is equal to Jn Qn bar. Similar things we can obtain for Rn inputs. Here we have substituted this place with the column of R inputs. Here this is going to be the pair 1 1. For this pair j is having two different value 0 and 1. So Jn variable is going to be drop out. K variable is having value 1. So Kn variable is uncomplemented. Here Qn variable is also having value 1 only and it is uncomplemented. So we can say that Rn is equal to Qn, Kn, Qn will be there. This can be utilized to prepare a logic circuit. The final synthesized circuit developed from these equations are shown in a figure 8.43. The functional block diagram within the dotted lines made up of SR flip-flop and two AND gates behaves like a JK flip-flop. Thus, convergence between the flip-flop in simple case can be done comparing the respective truth tables. For other cases, the steps shown above can be followed. So you can see that you are having basically the available flip-flop is going to be SR flip-flop. What is the S input is required? S input is required the output of AND gate from the characteristic equation. What is the characteristic equation? Sn is equal to one of the input is Jn, other input is Qn bar. So if this Qn bar is taken as one of the input of this AND gate, other input is Jn, then output can be connected to the S input of the SR flip-flops. Similarly, for the K flip-flop, SR flip-flop R input is derived from K and Qn. These two will produce the output of this one is Kn, Qn, and that is the input for R flip-flop. And that way, the SR flip-flop is now converted with this two AND gate as a JK flip-flop. It behaves like a JK flip-flop, and clock is given directly to this flip-flops. Example, the next example is also there. One simple example here is this. Show that how a D flip-flop can be converted to the SR flip-flops. Solutions. Not characteristic equation of the two flip-flops. Now there is a second example is given over here, that how we can convert D flip-flop can be used like a RS flip-flop or SR flip-flop. For that, D flip-flop is having a single input, and that single input using some basic logic gate we have to convert into two different input S and R, and that way this D flip-flop can work as a SR flip-flop. And for that we can utilize the characteristic equation of both the flip-flops. The characteristic equation of the SR flip-flop Qn plus 1 is equal to S plus R dash Qn, and for the D flip-flop the Qn plus 1 next state is taking the value of D after the clock pulse occur. Thus, we can replace Qn plus 1 in SR flip-flop with the D. So D input is equal to S plus R dash Qn. We get the circuit shown in a figure 8.44, which behaves like a SR flip-flop but made from the D flip-flop and basic logic gates. Method as shown in the section 8.11 also gives the same solutions. So the D input, this is your D flip-flop is there. We want to convert into the SR flip-flop. So what is the requirement? One OR gate is there, equation for the SR flip-flops. That is S, one of the input of the OR gate is to be S. Another input is the product of the two input R dash and Qn. That means you require one inverter here that is going to be converted, R is converted into R dash. And another input is going to be taken from this, Qn is connected over here. So this output is going to be R dash Qn. That is one of the input of this OR gate. Another input is S, and that output will be connected to the D flip-flop. So you can see that outside this dotted lines, it will behaves like a RS flip-flop. S input and R input, Q and Q bar will be there. This way we can convert a D flip-flop into the RS flip-flop. You can utilize as RS flip-flop using this gates also. Some questions is given over here that you can answer by studying this lecture. Question number 1. Why flip-flop convergence is needed? That is also described here. What is the basic difference between analysis and synthesis steps? That is also explained, and in my lecture also it is there. What is the difference between the state analysis table and state synthesis table? Studying the previous lecture and this lecture, you can differentiate these things. Thank you very much, friends.